So this video is going to introduce you to a important diagram that we'll use quite a bit in our energy transfer model, and that's something called an LOL diagram. An LOL diagram is just kind of a fun name for an energy bar chart. And the reason we call them LOL diagrams comes from when we draw them from scratch ourselves. We start out with a large L, a large O, and a large L. And so we'll get some examples of doing that in class. The purpose of this video is just to take you through those steps of creating them using a few examples from worksheet 1. So you'll see the 4 steps at the top here, but we're going to apply those 4 steps to several different scenarios. So for starters, number 1, we have this car that's compressed against a spring in our initial scenario, and it's at rest. And then in our final situation, that roller coaster car is at the top of a vertical loop. Our first thing that we want to do is to decide what's in our system. And when we're thinking about what's in our system, we're thinking about all the objects that are interacting with each other. One of the things that is mentioned in our guidelines is that we want to always have the Earth in our system. And so I will include the Earth in my circle here. We also have a roller coaster car and the track that it's on. They are exerting forces on each other. And then in my initial scenario, I also have a spring. So the spring is going to be a part of my system as well. Step number 2 is to indicate your reference level, or that point where the gravitational potential energy is 0. You could write this out using words, or you can put something on a diagram if you're given a diagram in this problem. This is a step that's really commonly missed in drawing LOL diagrams, but it's really important to show where you're considering the 0 height, so the 0 gravitational potential energy to be. So my reference level is going to be this height that corresponds with the bottom of the track here. Then we go through and we decide which energy we have at my initial portion and my final portion. And we want to think about what type of energy we have to start off with. So initially, it says that velocity is 0. And so I do not have kinetic energy. Initially, I am at my reference level. So I do not have gravitational potential energy. But I do have a spring that is compressed in my initial scenario. So that means I'm going to start out with elastic potential energy. And so I'm going to create a little bar chart here in how many blocks I give my initial energy is actually not important. So I'm choosing to do it with 4 blocks initially. You could choose 3, you could choose 5, you could choose 2. It doesn't make a difference how many you choose over there. Then we're going to take a look at the final scenario. In this case, it is moving at the top of my loop, and so it does have kinetic energy. It is also not at the reference level, and therefore it does have gravitational potential energy. In my final scenario, that spring is no longer compressed, so there is no elastic potential energy. And it tells me that it is a frictionless roller coaster track, so there is no change in thermal energy. So that means in my final scenario, I have both kinetic and gravitational potential energy. My initial energy was 4 blocks total. And there is nothing adding or subtracting energy to my system, and so my final has to be 4 blocks total as well. How you distribute those 4 blocks, or however many blocks you choose to draw, is not important right now, as long as there's 4 total. So I am going to choose to say that kinetic energy has 3, and gravitational potential energy has 1, and so those would add up to being the 4 total that I had initially. In my qualitative energy conservation equation, I'm just going to follow along and write an equation based on my bar chart here. So I have the initial elastic potential energy is equal to the final kinetic energy plus the final gravitational potential energy. In future problems, we'll then go one step further and actually do the math using that equation, but for now we're going to stop there. Writing that equation is a part of doing an LOL diagram. So make sure if you're ever asked to do an LOL diagram that you include that equation in your diagram. We're going to repeat this process again on number 2, but this time our track has friction. So we will have the same objects in our system. And we're going to choose that same reference level, the bottom of the track here. Initially, we still do not have kinetic energy. We still do not have gravitational potential energy. It is not moving, and it's at the reference level. But we are starting off with that same amount of elastic potential energy as we initially had. The part that's different is going to be our final energy. We still have kinetic energy. We still have gravitational potential energy. We still do not have elastic potential energy. But this time we are going to have a change in thermal energy because we know that friction creates heat. We still only have those 4 blocks to begin with because it's the same initial scenario. And so we have 4 blocks to distribute among 3 types of energy here. And if you think about it, in the real world, when we have friction, things slow down. That tells me I'm going to have less kinetic energy. How much less is not important. So I could do 2 blocks here, 1 block for gravitational potential energy and 1 block for thermal energy. But I want to show you a skill of something that we can do in case it ever comes up. Let's say that I wanted to put a half block on thermal energy. This is not the best way because sometimes it's really hard to tell if it's a half or not. And so one easy way to tell if it's a half is to do a triangle. Like I'm cutting that square in 2. And so my total amount of energy on this right-hand side would still be 4 blocks. I have 2.5 here. I have 1 for gravitational potential energy and a half block for thermal energy. As I'm writing my equation, I have that the initial elastic potential energy is equal to the final kinetic energy plus the final gravitational potential energy plus that change in thermal energy. I'm going to skip over number 3. That's a problem that I want you to attempt yourself. And I want to look at, actually, I'm going to skip over number 4 as well. And I want to look at number 5 because there is something a bit different about number 5. So in number 5, we have a person who's pushing a car to get it to the service station. We always have the earth in our system. And in this case, we have a person who is exerting a force on the car. And the ground is also interacting with the car, so I'll put the ground in my system as well. In my initial scenario, there is no kinetic energy. Oh, and I forgot. I need the reference level. So I want to make sure I define a reference level. And in this case, I'm going to say the reference level is the ground, just as we've been doing in the past. I have no initial kinetic energy. My initial velocity is 0. I have no initial gravitational potential energy because I'm at my reference level. And there's no springs involved here. So I have no initial elastic potential energy. That means my initial bar chart, my initial L, is completely empty. However, in the final scenario, it is moving. So I know that there's kinetic energy in the final scenario. I'm still at the reference level, so no gravitational potential energy, no elastic potential energy because there's still no springs, and I'm sure there's probably some friction involved here, so there's probably a bit of thermal energy. So let's say that I have 3 blocks of kinetic energy, and let's say I have 1 block of thermal energy. So the question is, where did that energy come from? It can't just magically appear, so it must have come from somewhere. Now, the whole reason this car started moving was because this person exerted a force on the car. So instead of having the person in my system, I'm actually going to put the person outside of the system. And they are exerting a normal force to give energy to the system. So this is where the energy flow diagram aspect comes in. I'd put the person outside because they're the one that is exerting the force, and I label what type of force it is, and I put an arrow that points into my system. When I'm doing my equation now, we've learned that work is the transfer of energy to the system. So the work done by the normal force from the person is equal to the final kinetic energy plus that change in thermal energy. We will do lots more practice with these and, of course, also go one step further in calculating quantities using this energy conservation equation.